Before I start anything, I think you all remember that our topic was on microwave and terahertz imaging. Many of you, and as Professor Umar told on the first day, that he would first try to explain the basics of microwave or RF imaging, which will include, terahertz from that perspective. So I will just try to briefly explain that what are the common components. If you compare, for example, RF, microwave, millimeter wave and terahertz imaging, these are electromagnetic waves. And also all of these, they facilitate the use of what we call the phenomena of radiation. They use antennas. So you don't need any physical connection between the medium which you want to image or test and the source. That's the basic thing, and that's also like what people, for example, if you compare ultrasonic imaging, typical ultrasonic imaging, you know that people come with some probe and they touch your skin if they want to take ultrasound of anything. That's like a physical connection. On the other hand, for example, X-ray. It's a typical example of the imaging where you don't need any physical connection between the object, the test object, test medium, and what we call the source. So if you look from that perspective, then you can say that the procedure, the basic assumption, what you can call the basic concepts, they would be the same. So there wouldn't be any difference. They are electromagnetic waves. You are trying to access the object from a distance. Of course, they mostly are what we call far field imaging, and as Professor Umar had mentioned yesterday also probably, that in far field imaging means you don't have any physical connection, and if you have a far field, you have plane wave approximation. So analysis becomes simple. Of course, we also have what we call sometimes near field imaging, which we will discuss today later on. So there are always pros and cons of both types of imaging. Whether you are doing far fields, which is contactless total, near field could be you have sort of contacting, but there are also advantage. For example, if you have far field information, then you can imagine the signal will be weak if you look from that perspective, and so from that point of view, it will be sort of difficult to retrieve the signal, because whatever imaging we mention, whether this is RF, terahertz, or even what we call the normal electromagnetic imaging, usually the method is so that you don't have directly or you don't facilitate the measurement of direct parameter. So you measure something and then you use a sort of procedure in order to retrieve the actual parameter, and that's why usually it's inverse problem what we call, because we don't have a way or method to directly measure the actual quantities. So today I will just try to briefly explain first that what's the commonality between terahertz, RF and microwave, and then we will slowly see terahertz is today a buzz term, everyone uses terahertz. It has advantage, but not everywhere. There are still many applications where terahertz can be used. At the same time, there are situations where terahertz can be advantageous, but with the knowledge that you have to keep in mind that it can be used for everything or all the things whatever you want to aim for. So many things they look fine from theoretical point of view, but they are not that practical if you go from to the other aspect. This is the full electromagnetic spectrum, as you know quite well. So as you can see, if you go from radio wave, microwave, this region is sort of millimeter wave. If you see, this is a terahertz, 10 power even 10 power 12 gigahertz. So basically that means you can see that point, this is 1 terahertz 10 power 12 hertz. That means if you have any electromagnetic waves having frequency from 0.1 terahertz to 1 terahertz, we can call them terahertz. And that is why even 100 gigahertz, if you do a measurement, or 120 say, you can say it is 0.12 terahertz, and that because, and why people do this? For a simple reason, that keeping in mind that theoretically they are similar as compared to microwave or millimeter wave, but it is not very easy, at least from economical point of view, to have setup for measuring signal in terahertz range. That is the main challenge. The components are expensive, source is not that easy, setup what we prepare is not that what we call cheap, and also not very viable. Now you know what is the range of millimeter wave? When we say millimeter wave, what is the frequency range? Usually, anything let us say below 30 gigahertz or more, you can say is millimeter wave, because it is on the order of millimeter, because microwave is centimeter wavelength, and the where you say it's 1 millimeter, this will be sort of 30 gigahertz, you say now it's millimeter wave. That means somewhere in say here microwave, but actually this region is millimeter wave. That's why sometimes they also called sub-millimeter wave. And this is something which we talk as electrical engineers. If you ask physicists, they call it far infrared region. For simple reason that they see infrared region, and if you go beyond this, you can extend a sort of from here to here. And that's actually very interesting aspect, depending upon whom you talk, or whom you talk to, whether you to electrical engineer or physicist, because usually the idea is simple, that physics people, they usually, for example, work in optical and infrared region. So they thought, okay, fine, I can apply the same concept a little bit far. That's why they will call it far infrared region. If you are a microwave engineer, you say, fine, we work up to millimeter wave. Now it's sort of same concept I can apply a bit far and say, okay, some millimeter wave. So that way, if you see, even before this terahertz became a buzzword, people were using sub-millimeter wave and far infrared region, both electrical engineering point of view and the physics point of view. Especially physicists, they were using it quite often. And you can see there that 1 terahertz become around 300 micron, which you can say 0.3 millimeter. So this is like a sort of sub-millimeter wave. So that's something, and that this sub-millimeter wave or far infrared term is actually very interesting, for simple reason that you can apply the same concept what you apply in millimeter wave to sub-millimeter wave, and that's why people use to call it sub-millimeter. Similarly, the people who are working with infrared sources, they say, fine, if I go a bit far, I can stretch the same concept to what we call far infrared region. Once you understand that this is something what we are talking about in terms of the frequency range, so now as Professor mentioned, any imaging is what we call the resolution, which is proportional to the wavelength. So it basically means if you go from 10 gigahertz to 0.1 to 1 terahertz, the wavelength starts reducing. And so it means that if you are microwave engineer, and if you work in microwave and millimeter wave imaging, the main motivation and the main advantage of going from millimeter wave to sub-millimeter wave and terahertz range was that you can try to have better resolution, because wavelength will be reduced. That is the main what we call motivation, which was the reason for imaging, that if you go higher and higher up in frequency, wavelength is getting reduced, and so you have what we call the better resolution. and that's like very, of course, if you compare with X-rays, you have better resolution or worse resolution. It will be worse. X-ray is still higher, but X-ray being layering is ionizing, so that's why terahertz is still non-ionizing. That's also the advantage, that without going into ionizing region, you are able to obtain so much resolution. That's something that you have to make a balance. So this is it's just a simple concept that if you have a low frequency, then you have the wavelength is very high, and so you can have what we call current and voltage static approximation. And if you go to higher frequencies, millimeter wave, wavelength and beyond, you have to take into account the phase delay, and you have to obtain electrical magnetic field. So this is just like you do for any kind of RF, millimeter wave or terahertz. So the main thing is that if you go from higher frequency, you have better resolution. Now let's try to let's understand something basics from the practical point of view. So as Professor Omar mentioned yesterday, when you start, let's say 0D imaging, means you have a homogeneous material having the constant permittivity. So if I take a rectangular block of one material, it's like a homogeneous block. Now you can call it imaging. Now let's understand one thing, that let's say I take this rectangular block, and if I say this is homogeneous, assume that there is no change. So I can call it 0D imaging, but I can also call it what we call the characterization. So now the point is that when we call it characterization and when we call it imaging, assuming that material is homogeneous block of fixed dimension, that's something very should be very clear in mind. So when I say characterization, it means even if that means in this aspect what we call the characterization, we know the physical dimensions. So if someone gives you, I want this IV block, rectangular block, I want to know its permittivity. So he'll give you the thickness of the object, he'll give you the height, everything is given. So now that means you have more known parameters, the only unknown thing in this case will be permittivity. The problem is easy. So that means when I say characterization, it means that you only need to know the electrical parameters, the physical parameters, they are known, whether it is thickness, it's a height, it's the whatever you have. So that way you can call that it is the first step in imaging. Of course, here also you have to use electromagnetic waves. So depending upon material dielectric or magnetic, but they are electromagnetic waves, and you use these waves in order to find out the material properties. So usually this used in the context of materials. So we don't say object, it's a material. Though that means someone gives you like, oh, this is, I have no material, I don't know its properties. And also in this case usually it's important that you try to find out or estimate its property at any frequency. For example, could be I have one block, but its property at 1 gigahertz different from, let's say, 100 gigahertz. So if you really want to characterize the material, then you should know that at which frequency you are talking about and what will be the value. On the other hand, if say you want to find out the image, so in this case your main interest is that you want to determine the spatial distribution. You want to know that if you go along x or along y, how the permittivity changes. Ideal thing could be that you could obtain both, but you know it's difficult and not very much sense, because if you try to recall, a spectral domain is the frequency, a spatial domain is the distance or time, and there are two independent domains. That's the whole basis of all the transform, Fourier transform, Laplace transform, all the transform. So it doesn't make also much sense to say I want to find out permittivity, I mean the distribution of permittivity at each frequency, because frequency or spectral domain is just virtual domain. Actual thing you want to know that okay, the distance or time. So that's why when you say characterization, it makes sense to say that this is for materials. We can assume it to be uniform or homogeneous, but sometimes also for simple characterization we can also say it is anisotropic. So anisotropic and uniformity, they are two different things, right? What's the difference between the two? So non-homogeneity means there is change with the distance. Option R could be definition of x, y or z, but when we say anisotropy means it's a direction. So it could be that you have x, y or z component, but there is no change. This is something you have to understand. So for characterization, you always assume material is homogeneous and uniform, but you could imagine that this is like anisotropic. That means, it's, for example, if you consider Cartesian coordinate, I can say epsilon along this direction is different from this and along this. So you can have say 3 independent components. So that's way, and that's possible for the characterization. And for example, and if you have something like, let's say, like a wood, for example, you can call this anisotropy, which is sort of uniaxial, because just like you have one this direction and the this direction. So that is also what we call the anisotropic but simple anisotropic material. So as I mentioned earlier, for characterization you know the physical dimensions of the object. Either you know it, or I mean, if someone gives you this object, I can take a scale and I can measure. Oh, this is x, this is y, this is 2. So this is known. So that is, but the point is that this is the first step, and it is simpler than what we call the imaging. If you go to the other step, so for example, now if you come to imaging, now you have the same block, you don't what we call, so let's say you are not able to measure its length or its thickness or whatever you can call. So in this case, what can you do? Now you have homogeneous block, but you don't know its length or height, or it's a cube, you don't know its, let's say, parameter A. So now your object is that you are looking at this object from a distance, you come with your source, and whatever information you can take, this is your choice. But I would like to know, for example, let's say you don't consider this object, now you consider that we have this object in a domain which is surrounded by this much space, and also let's say in this I put some other object. So this object is hidden now. Now I don't know where is the object, and I don't know its location, I don't know its, although it is homogeneous, but I don't know anything about this. I don't even know location also. So I want to detect the object, and also I want to know what are the dimensions. So in this case, even if the object is homogeneous, and if I can do some measurements around this thing, even if it's hidden, so at the end I should be able to know its electrical properties, let's say permittivity. I should be able to know where it's located, and I should be able to know approximately what are its dimensions. Then it will come in the context of what we call the imaging. So we use, and I am using term RF radio frequency, but it could be RF, microwave, millimeter wave, terahertz. There is no difference, depending upon what's the frequency of the electromagnetic wave which you are using to obtain the information. Everything is the same. So I mean, like if you have terahertz source, you can still go with this terahertz source. You can try to scan whatever information you have, and then it will be terahertz imaging. So that way, if you see, there is no, I mean, difference whether you take radio frequency, microwave, millimeter wave or terahertz. But the main point is that you would like to know the location of the object, its physical as well as electrical dimension, and that's something actually you have to understand. So if you have to use RF and terahertz waves to obtain dielectric image, and image here means that you can differentiate the region by the dielectric properties. For example, this again very interesting to see that you have an object, this is having let's say Teflon block, perimeter is 2. However, if I put in the free space and if I want to know its location, the best part would be that if I look area around, it is air, permittivity will be equal to 1. So, if I am able to know that if I go from this point to this point, wherever there is a interface between air and the object, I can see clear distinction. Like, oh, this is air and this is this. That means I can consider this as a sort of simple two-dimensional or simple say two medium object, that in one medium is air, this is what we call block, is again air. So, if I am able to find out in this case material properties as a function of distance, if we go from here to here, then I can say that this is the dimension, because here we have a change in the permittivity, and also I can find out the permittivity of this. And again, when I say imaging, it can be qualitative, it can be quantitative. When I say qualitative means I just want to know whether there is some object. I am not worried about its actual permittivity or permittivity whatever. I just want to know that I have some medium and whether something is hidden inside. So, and for this is enough that if you try to scan this area and if you say in this region there is something else, what object is there we do not know, but it is not air, then I can call and you are able to approximately find the shape. Then I can find out that okay, then this is I can call a sort of qualitative imaging. That means we just want to know the object location and we are able to detect the object, that is enough, we do not want to know details. However, if we say imaging is quantitative, it would mean that apart from knowing its object location, apart from its detection, we also want to know its dielectric properties. That we want to know that whether it is Teflon block or PVC block or wooden block, what's the material. Then again that is something one step ahead then, but when you say we just want to have find the object. So, qualitative, quantitative, so that means if you go step by step, first for the characterization, just want to know property, then you went to imaging which is qualitative, and then you want to say quantitative. So, all the things depends that what you want, what's your objective, what you want to know, and of course, if you go further steps, then you have more complication, and that basically means that in this case you have to actually try to find out that you need more data in order to extract the information. That is something which you have to put in mind. So, as I mentioned there, in this case you have to have a thing where which is non-homogeneous. In this case also you can say, if I consider air as a medium, so I can say air, dielectric air. So, this is like a 3-layer media, and so this is also in one way what you can call non-homogeneous. So, that is something that you should try to understand. It could be in longitudinal or what we call the transverse. For example, longitudinal means you go from here to here, transverse means if you go from here to here. So, it could be in any dimensions. This is again very important, that whenever you have imaging, you are only allowed to perform measurement at the surface. So, you can go and say, so this is a homogeneous block, but suppose or let us say I put something on the top, so I am only allowed to do measurement at this point. I can go and directly measure here. So, that means from this point of measurements I should be able to know that if you go along this direction, this is so much is air, and then you have the object. So, this is something like which is again a case of any kind of imaging, that you only have measurement at the surface, and from this measurement you want to know the object properties, whether qualitative or quantitative, and you do not know the physical dimensions. For example, here I do not know the x or y. So, this is some.
We want both qualitative and quantitative property. Then there will be multiple number of solutions. So, how we are going to choose the definite
Yes, there might be multiple solutions, and that is why, as we mentioned earlier, this is the inverse problem. So, then you have to apply some more condition, what we call a priori information. this we usually call a priori information, or if you see in mathematics, we say what we call, you have to regularize the problem, what we call regularization. So that means, you are right, it's not easy to solve the inverse problem. That's why, I mean, it might give you no unique solution. So even sometimes maybe the matrix which you have, you cannot actually do the correct inversion. So problem is both on the mathematical front and also on the practical front. Practical front is that signal might be very weak. Now if the signal is very weak, how to get the correct information or how to get the correct image? That's a problem which you have challenge on the practical side. On the theoretical side, it's like, because it's like inverse problem, you want to invert the matrix, so it might not be easy. If your matrix, for example, is ill-posed, you can do anything. Then that's why we call it that we have, if you have some a priori information, put it there, or let's say you put some sort of regularization parameter, what we call, so that solution is what we call stable. This is something usually we do it. Yes.
In this case also we have to consider the entire medium as anisotropic without directional properties like characterization.
No, you don't have to.
If there is any directional property of,
yeah, so that if that is the case, it makes it more complicated. So as I mentioned there, even for characterization also, simplest thing is you have isotropic, homogeneous. But for characterization, if you still have anisotropy, that's not that complicated, because you still have homogeneity. You just have say you have, but here for imaging, the main thing is what you call a non-homogeneity. Anisotropy here is not that thing, because you know that imagine that you want to know distribution of the permittivity as a function of x, y, and z. So this is the main thing. Though here anisotropy is not that the important parameter. Okay. So this is just like if you have a, this is the main parameter for the non-magnetic medium, what we call the permittivity. And sometimes what is important is that we define imaginary part as also effective conductivity. But that's to say that it can have both dielectric and conductive losses. So this is just the mathematical expression. So this is just like, you know, that I won't go in detail, but this is like, even if you have characterization, you have many applications. One of the things that nowadays all the devices which are planar, antennas, what we call filters, circuits, MMICs, everywhere you have substrate. Substrate is dielectric. Usually if you buy a substrate, they will give you the number. FR4, 4.4, 2.2 or something. It works. However, if you really want to know have very accurate design, so you have plus minus 5 to 10% tolerance. And now if you do everything right, and if you don't, and if you really especially do something for static application, you want to know very accurate design. For this case, actually it's very important that you measure the parameter at that frequency, because then do everything and you still have, let's say, difference of 5 to 10% in result, you don't know what to do. So, and the reason could be you are taking not correct value of the option R, and without correct value of the active constant, you can do any analysis, because any software use CST, HFSS, whatever thing, you have to give the dimension of the parameters. So that's also very important aspect, that whatever thing you want to test or you want to design any planar circuit, you have substrate is dielectric, and so it's better that you actually measure its property at that particular frequency. That will give you more confidence in the design of any planar circuits. And the same concept now, that if you want to know this dielectric image, so that means now we are saying that rather than having a homogeneous thing, we are having what we call the non-homogeneous materials. You know, it has from agricultural science, if you say different food grains, they will have, so it have, you know, if there is, if you go and search the website, there is in this, for example, US Agriculture Agency, they have a full group on this microwave characterization. What you do is that they just try to find out material properties of various food grains. One thing is that you can distinguish the material. Other thing is also that you can directly correlate moisture content with the food materials. So that gives you the food quality. For example, I have some storage for grain, and without going inside, I want to actually know its condition, that what will be the condition of this particular material. So what I can do is that I can keep on monitoring its permittivity as a function of time, and the concept is simple, that if the grain is not good enough, it will go moist and it will have low permittivity. So that means if you are able to determine the permittivity, then in principle you are able to find out the condition of the food which is being stored without going inside. That's something which is when people use it in order to what we call the for agriculture applications. For concrete structure, as we see, this is again very interesting area which is being used. So idea is that concrete, when you make it, so usually you first make it by adding this different kind of sand and everything, and then you want to know its condition, a function of time. So the usually, for example, it takes 24 days or so to dry it. So microwave is advantageous because you can just use microwave in order to find out the condition of inside concrete without doing any damage. So you just take one antenna and you try to scan this, sort of what we call health monitoring of structures. This is, you can use it microwaves for that applications. So you can just find out, say that okay, what's the quality of this concrete, and again the concept is same, that if the moisture content changes, it changes the permittivity, and permittivity you can determine using microwave method. So that's again very good applications. Yes.
In previous slide you said that measurement of like in motivation, measurement of permittivity of terahertz material. So using imaging, but like what is the advantage of using imaging over a conventional method of measurement of permittivity in case of dielectric material?
No, I didn't say you use imaging to find out the permittivity. What I mentioned, that characterization is one aspect or the first step towards imaging. So if you have a substrate, usually people say it's homogeneous, right? So you just want to know its permittivity and you know its thickness. For example, if I take 5, I know its thickness is, let's say, 1 mm. So I just want to know its permittivity. So it doesn't come under imaging, it just comes under characterization. This is, but what I mentioned, that this is also important, because if you don't know its permittivity, actually you can go to the next step, which is the imaging part. So this is something like, apart from designing of normal circuits where you need this permittivity value using any method which you know, if you also want to use imaging, then you can only distinguish different regions by the permittivity. So if you don't know its permittivity, you can distinguish. So that was my point. Okay. So for geological application, this is again what people are trying to explore. The concept is again very simple, that if you normally you have water inside. So if you go and scan the area with microwave, so it will give you normal signatures. On the other hand, if there are some potential area of hydrocarbons where you expect that there is some oil in that area, the good point is that water and oil, they have very sharp change in permittivity. Water is around 90, oil is around 2 and 3. So there is a big change. So concept is the same, that if there are some potential areas of hydrocarbons where you expect that it is like what people call bituminous soil, to say that this soil could have some hydrocarbons or water content. So there again, without doing much damage to this, if of course the point is that how far you can penetrate, that's the other aspect. But if you could penetrate enough, then actually you could try to sense that this area is it's not having water. That means it may be having oil. That is the first step which you can test using what we call microwave. And this is also, for example, company like Schoenberger, they are having this method to explore that, okay, where is the area where you can expect hydrocarbons, and this microwave can be used. Again, sort of microwave NDT or imaging, because you can use microwave in order to scan the area or to find out the oil things. Biomedical, probably also Professor might explain. This is again very potential areas that you try to image different tissues using what we call microwaves. So especially soft tissues. And why people are interested? Simple reason that X-ray is ionizing. So if you can use it, the only problem here is for biomedical is that it's difficult to penetrate the skin, and that's the real problem. Because skin is having very high value of permittivity, so if you go from air to skin, you have maximum reflection from the skin itself. So you are not able to penetrate. And if you don't penetrate beyond the skin, actually it's not easy to get information which is subsurface information. There are methods for this. The method, if you see, is not much different from what people use for ultrasound. If you use ultrasound, you have seen that people put some gel before they put this thing. And the idea is just to sort of do some impedance matching with your probe to the skin, so that like the ultrasound can go inside. The same thing people are trying, that if you want to do it for biomedical thing, you can use water or some other medium, and I can use, let's say this, I want to image my hand. I can put my hand in water, and then I also put in water. So now, compared to water, my skin is not having very different properties. So that means this now microwave can penetrate better. That's like sort of impedance matching between the background and our skin. That's something people are trying to explore. That way you can penetrate more, and that helps in micro imaging. But it's not fully mature technology. This is something actually people is very interested, but we call security applications in the airport. And actually, if you go to some airport in US, they already have what we call millimeter wave scanners. And this is simple because it's microwave or millimeter wave can easily penetrate your clothes, because they are simply like they are not having glossy material. That's actually very good application that people have been using, and Terahertz also is a good application, because your clothes are very thin, and even Terahertz can penetrate beyond the clothes. So anything is hidden behind your what we call the clothes, you can detect. There is a very good application of which is also having much potential in the future. Whereas millimeter wave and Terahertz, both are actually good application for this. And of course, the advantage is that again now X-rays are used which are ionizing. And second point is that sometimes X-ray can detect everything. For example, if something is non-metallic or plastic, it's not very, and it's also there is a second point what we call the detection of anti-personnel mines. Usually people used to have what we call metal detector in the past to detect this, because they all were metallic mines. But now there are many plastic mines. They look like normal plastic. So if you use X-ray, they will say, oh, it's some plastic object. But the point is that they are actually mines. And there is very good application for millimeter wave or even Terahertz. With a simple concept that if you they look like plastics, but as compared to normal plastic, they have different dielectric signature in millimeter wave also, and also in Terahertz. So that's something actually very good application of this. So and this is actually one of the potential areas that people expect where you can use it practically, because there is not much difference as compared to the biomedical. This is just an example to show, this simulation thing, that if you have a tumor in thing, again tumor will have different properties than the background. So that's like you can actually in principle detect tumor, because it will have what we call different moisture content, water content as compared to background. And this is actually also less expensive than MRI, and you have no ionizing radiation. Of course, again the problem is that you have to put it in a particular background medium. But in principle, you should be able to see this, because it will have different dielectric properties. But this is what people, and this is the good point is that this can also be used to detect cancer at early stage, what people call the benign tissues, not even the malignant tissues. This I mentioned that for NDT in swinging applications you can detect voids and cracks inside concretes. Again the concept is, yes. Tumor differences was? This was 2.45. Yeah. So, so for swinging applications, actually you can detect invisible damage. Concept is simple, that if you have any crack inside the building, you cannot see with naked eye, but if you use microwaves, so because you have air has different properties than what we call the normal wall properties, so you can detect. Similarly, if you have something you want to know, people put some steel bars inside. Now, sometimes people forget that where is the steel bar. Only way that you go and actually cut it. If you use microwaves, it is, or millimeter it is more advantageous, because if you just go and scan the area, let's say using a simple millimeter wave antenna, you can see that wherever you have what we call the metal bars, it will give you very sharp response. That's also one of the possibilities with people. So you can use steel bars, or you can find location of the steel bars. But these are all things is possible using millimeter wave. And this is people are trying. This is not very difficult, because concrete walls, they are not lossy. So you can microwave can penetrate inside. This is, yeah, so idea is simple, that air void or steel part will have different properties as compared to normal background. And also this, what is coming in by RF sensors is again a sort of not, I will explain this afterwards, that where can be used for imaging. So airport security, this is something like people have been trying, that you are working with this and something you hide inside, so you are able to get the image. This is something people have been using millimeter wave scanners. So this, if you want to go there, is already available in the web. So as compared to, for example, infrared or visible thing, microwaves are preferred because they can penetrate more. And this, as I mentioned there, that they can underground hidden object can you detect. And also even if plastic, you can detect using this explained. Now, just very simple thing, that this is just for the background, what all you can do and what all you cannot do. Now you should understand that whether you have RF, microwave or terahertz, let's say it's a simple same thing, homogeneous object of same permittivity and this thing, but you don't have any mechanism as of now that you can go with your device and you measure permittivity at each point. This you don't have. What you can measure is reflection and transmission coefficient. This is as if you have done the microwave measurement, this is that this is something which you can measure. Is there anyone who had not done any microwave measurement, or have done some microwave measurements, right? So usually at microwave, you measure what we call scattering coefficient or reflection and transmission coefficient. Same thing also for imaging, because whatever instruments you have, most common is what we call network analyzer. So you can only measure what we call reflection and transmission. Now it's your job that using reflection and transmission coefficient, how can you retrieve the material property or the object image. Whatever thing you want to know, whether it's characterization or imaging or anything, the only thing which is available with you is reflection and transmission, amplitude and phase is a function of frequency. So you can vary the frequency. You can also measure a number of locations. All these things you have, but by doing this measurement, you cannot directly get the permittivity. You have to use some method, and that's why we call this the inverse procedure. This is just to show that if you have air, this is 1 and matter is also 1. So this is a simple concept. So the steps. So this is just if you have not worked in the past, this is a very simple thing, that what are the steps you use practically for imaging. First of all, you need to develop a forward model. Forward model means you have some equations which gives you an idea that how you can measure scattering parameters, or how you can not measure, I will say how you can correlate scattering parameters which you can measure with the properties that which you cannot measure, like electrical properties or the physical properties. This is called direct problem formulation. That means if you want to start the imaging, whether it's 1D, 2D or 3D, the first thing which you have to seek is that you have to get some equations. The equations which can give you a relationship between the known quantity, which in this case for example will be a scattering coefficient, and a known quantity which could be your permittivity if it is homogeneous, or permittivity function of distance epsilon r x if it is non-homogeneous. So this you have to, without this you can't actually move. Now once you have an equation which describes that how you can relate scattering parameters with the electrical properties, then comes the next step, that how to measure. Without measurement you can't do anything, and it's also again not very straightforward, because depending upon the situation, whether you want to image, for example, concrete wall, you want to image object inside the inside what we call the earth, or variable things. So you have many situations, and that's why the second point is that you have to establish a setup which facilitates the measurement of reflection and transmission coefficient in a given actual real scenario, not like in a lab, because at the end you want to image something on site, on the real in the real medium. So it's very important that when you try to image, or when you want to image any test region or test medium, you have to see that what is the viable setup which can be used in order to measure the scattering coefficient. And once you are done with both of them, the next part, what we call development of some algorithm, which we call inverse regression algorithms. Because at the end you have done measurement, you have equation, but that's not enough. You have to what we call the data should be processed properly, or what we call interpretation, and this is something like what we call the inverse algorithm. That means you have the measurement with you, you have the equation, now you have to find out that in what way I can try to process the data so that I get, for example, permittivity image of the object. And there actually is again very complicated situation. It's not that straightforward, because this is the inverse problem solution. It might give you a non-unique thing, might give you ill-posed problem, might give you matrix inverse, not that easy. So there it itself is a big research. There are many people who only work on this aspect. For example, this is like more like signal processing part. So many people, they only work on this aspect from mathematics, from signal processing thing. Without knowing anything about the microwave, they say, okay, fine, I am trying to work on the algorithm which works, which gives a stable solution. That itself a big research field. But if you are able to successfully do this, then in principle you are able to get the image, whether in RF or terahertz, of the object. So this is, I mean, as a thumb rule, that's something actually which is very interesting and very important, that you should be able to obtain the image of the object or the medium by using all the 3 steps. It looks simple, but when you start doing this, it's not. So it is like a lot of steps are involved. Now, so far just the background, and you have seen, I mean, especially from the practical point of view, that what all things you needed, you need it for this. Now, before I go to that, let's try to see, and all the things whichever I have explained, they are valid for RF, millimeter wave, microwave, terahertz, because you cannot say anything which is say is only for microwave, only for terahertz. The concept are the concept, and they are the same, whatever you want to do, except for the measurement part. There something will be different, because for the measurement you need a source, you need a setup, and as I mentioned earlier, terahertz sources, terahertz equipments, they are not that easy to get. Reason is simple, that terahertz like microns, anything dimension goes smaller and smaller, it's not easy to fabricate, because you need a lot of sophistication, and that's why they are expensive. So they both have electromagnetic waves, so that way there is no difference. You obtain the image of the object, Also it could be quantitative or qualitative. So this also is no difference from that. Could be non-homogeneous. This I explained earlier, that if you just want to know the qualitative, means you just want to know the where is the difference, and here you want to know the permittivity or permittivity. Now this is something actually very interesting. Resolution we discussed that if you go from millimeter wave to terahertz, what is the effect on resolution? Resolution is better. However, as I mentioned earlier, this is very important part, what we call the penetration depth, because if you want to image the object, you want to penetrate. You don't want surface image, you want subsurface image. And subsurface means, for example, imagine that I have some chalks inside. Now I want to know what is inside. This is subsurface. It's just like a box. So unless I penetrate inside, I can't know what is inside. And then comes again the same point, that how far I can penetrate. And there is the challenge, that if the frequency goes higher and higher, the capability to penetrate beyond the surface goes lower, and that's a trade-off. And that's why I mentioned earlier that terahertz is not solution for everything, because if you cannot penetrate, nothing works. I mean, whatever image you want to have, I mean, you have to first go inside. If you don't go inside, you can't see anything. And terahertz has this problem. Even millimeter wave has this problem if you go higher frequency. So typically, this I explained, that resolution is final if you go higher frequency, low what we call this thing. However, this is something what we call the penetration depth. This is approximate formula, and here actually what you can see, that lambda is in the numerator, and so if you go higher and higher in frequency, lambda go low and low, and that means you have very low depth of penetration, and that is the challenge for millimeter wave, sub-millimeter wave, and terahertz imaging. And that's why there is a trade-off between resolution and what we call penetration depth, that how far you can go. And that's why, although terahertz is a fancy term, but practically if you see which are being developed or which people are working, microwave and millimeter wave imaging is still, they are more in demand because they are more practical. First thing is that they can penetrate more, and second thing is that still they are economical, they are not that expensive. So it can be applied for application where you actually without much expensive things, and they work.
So we can go for hybrid approach. For penetration, we can lower the frequency. For resolution, surface imaging, we can go for terahertz.
Yes, you can, provided that you have so much money to buy both terahertz and millimeter wave. Yeah. But in principle, yes, that's true. So terahertz actually people are using mainly for the surface, for the skin sort of imaging. That's also the main thing that people use, because you cannot go beyond the skin. A sort of skin thing you can still use. Yes. This I mentioned earlier. So this is again same thing, but from different perspective. So usually what we discussed, that you measure data in frequency domain, S11, S21, they are function of frequency. However, you can equally measure data in time domain. So for example, if you have good quality time domain spectrometer, you can go with this, and you can, and so then what you need time domain pulse. So basically you excite that object with time domain pulse, and then this is just the first excite, and this is then you get many peaks. This is the first peak which you get from surface, second peak get from next surface, and then this might be again goes and forth the next level of reflection and so on. So this is the one thing is that you have a time domain spectrometer where you go with your time domain thing and you measure this. But now, rather than going with time domain, is also you have what FFT or I50. So if you go and buy any modern network analyzers, they have inbuilt time domain facility. So what will be the challenge? Let's say if I want to have good quality time domain data from measurement in frequency domain, what should be the requirements? For example, I want to, because basically, ideally you should have impulse, right? Impulse we can get, we have something like this, or approximation something like impulse. But then what are the conditions which we need if you really want to have good quality time domain pulse?
High sampling.
Huh?
The sampling capability of the instrument in any signal.
In the time domain also it should be.
No, but we are measuring in the frequency domain. What I think that we have normal network analyzer and we are measuring in the frequency domain and we want to use the time domain data. So what will be the challenge?
Large frequency, but many frequencies are required.
Wide bandwidth. The main simple thumb rule that if you go wider frequency, first go narrower and narrower. So ideally would be that you have a very wide band antenna along with wideband network analyzer, and then you can have what we call the very narrow pulse. And narrower the pulse, better resolution in space domain. And that's why typically you can see that if you can measure over a very wideband data, then it leads to very good spatial resolution. This is also the again same concept as the normal FFT or I50 or frequency for your transform, that if you have a wideband measurement in the frequency domain, you have a very good resolution in the time domain. Their time and space actually they are the same, because if you see that they just depend upon the velocity. So this is something like which is typically being used. And so the idea is that nowadays without using what we call explicit time domain spectrometer, if you have a network analyzer which works over a wideband and if you have wideband antenna, it can equally be applied, because then you simply take I50 or you simply do achieve time domain data and you can get something like this. And time domain measurement is having many advantages compared to frequency domain, because time domain is a real domain. For example, let's say I have this kind of block and I am exciting from this side, and I have an antenna which works about 40 gigahertz, and so a network analyzer. So, and if this is quite thick, then even I should be able to get many such peaks at the screen. And from these peaks, what we can see, for example, at least I can see that okay, the first peak will correspond to the first what we call discontinuity between this and the background. So if, for example, if you know if you know its dielectric properties, I can know its thickness. If you know its thickness, I can go with dielectric properties, but without doing anything. So that's actually, maybe it's approximate, but at least it's very simple. That's actually the advantage in working in time domain, provided that you are able to get. Of course, there are also challenges, because sometimes you can see many peaks there and you are confused. If some expertise or no, it's just like some bird. No, this is again, so that's the same thing here. That if you are experienced, you can know that which peaks correspond to which kind of situation, or whether this is the actual peak or this is the, for example, it can also be that the peaks come and forth together. So maybe there are many other peaks which corresponds to many other things. So that also is very important aspect to observe. Now, whether you do this for microwave or millimeter wave, what is simplest thing you can do is, for example, imaging aspect. If I see, so this is like, let's say any object in the background, and say let's say I have different regions having different shapes, different properties. So there are actually different scenarios. For example, the simplest thing could be if you could have antenna having very narrow beam, then what you could do is you can go and scan the whole area, because of course if your antenna beam is quite large, then it might be that you are don't have many points, but if you have like a point beam, and if you could scan the whole area, then you should be in principle able to find out permittivity as a function of distance at each of these points. And that means if you are able to achieve this, then from the after measurement you can have data processing thing, and you should be able to find out that okay, in this region there are 3 objects of different shapes and different sizes, and this is how they look like. So this is like sort of you can say that narrow beam source which you can scan, and that can give you the area, and you can do a scanning somewhere here, not necessarily directly. It is the same way I mentioned that some object is hidden inside. Without opening the box, I can scan at the surface, and I can know that what are the things written put in there. Provided that, for example, suppose this is an antenna, then I can simply go and scan. Like of course, it's not easy to have antenna like this, but if you could have this, it's very easy. So as I mentioned earlier, for subsurface image, you have to have some inverse algorithm. This could be iterative, could be non-iterative. Non-iterative means like you are looking for some closed form solution. It's not easy. It might work for simple one dimension with many constants. But the advantage of non-iterative thing is that it takes less time, it's stable, it's closed form, and it gives you some idea. But disadvantage is not accurate because you have many approximations. So the best thing, if you see practically, is that you combine. You combine, for example, as I mentioned earlier, any numerical, the common way is what we call iterative solution, that you try to make solution, you make error function, you minimize the problem, but then problem is again that how to get unique solution. And for this, if you have good a priori information, that you know that you are close to the solution. So in this case, if you think the best way would be that you use some non-iterative method, which is a closed form solution. You try to obtain approximate image, and then you iterate. So that way you are close to stability. So what you can think of, that we are trying to provide some a priori information to your algorithm, which helps you to obtain a stable solution with reduced time and also with more stability. So that's something actually people are trying to do. But this is the thing which you have tried to obtain. And of course, as I mentioned there, that once you develop algorithm, you have to facilitate the scattering coefficient, the surface, and so on. This I mentioned there, that you can have a scanning arrangement for this, and this can give you the object inside the location. This is something like, you can think of in a scenario that if you could scan the area, so you can go on scanning this, and also you can try to put, for example, top. So basically it's a 2D thing. So, and also you can try to scan at different depth. This is like, this will help you that to obtain more information. Now, coming to terahertz. If you know, it started for space applications, and actually for space it was for many decades. It's not new. Radio astronomers and these people who are working in this program, they use it even in 60s and 70s. It's just like now they started using for the commercial application. So for space application, actually, what's the difference? You have very low density and you have very less moisture. So it is perfect. Terahertz is why terahertz were used, or what we call the far infrared or some millimeter wave. They were being used for space application in the high altitude for many decades by space scientists. Reason was simple, that there you have very low density and low moisture, and you don't have very low terahertz attenuation, and so that is perfect situation. And so you could, so there were two. First thing is you have low attenuation, so terahertz will not attenuate, so you can get terahertz can penetrate in the regions, The second reason is what we call the here radio spectrometer. Most of the photons which are emitted naturally, their frequency rise in terahertz region. You know that the big telescopes, they are passive imager, they are not active imager. They just detect something from the space, from the terrestrial regions. And physicists and scientists, they have discovered that since this what we call Big Bang day, all the photons which are being emitted naturally, they are in sub-millimeter wave and terahertz region. So there are two main motivations why people started using this terahertz and sub-millimeter, and they are not, it's not new, it have been for many decades. So that way, if you ask any space scientist, they say, oh, for us it's not something new. It's only in the recent years that now people try to explore whether we can use the same thing also for ground, for Earth. And there it's not yet fully compatible because of the challenges. The challenge is the same, which is actually here the advantage. For example, you have less moisture, that's perfect. Once you come to ground, moisture is quite high, and you have quite high terahertz attenuation. And then everything, whatever you think of high bandwidth and very low, very fine resolution, that all goes down. Because even also for communication purpose, people thought of, okay, we can make terahertz link and everything will be very high quality. But the problem is that just beyond 100 meter it can go. So even 5G for millimeter wave, people are thinking what to do because of putting many repeaters, as Professor was mentioning. So terahertz is something one step ahead. So then how would you realize practically that if you have a range of 100 meter, I mean, what can we do with this? Except, for example, like let's say in something like at the local airport or something where people could try, but still it's not yet commercial.
So the third point is regarding its operation or instrument health, low density atmosphere, or biting the instruments of advantage?
No, this is the actually advantage.
In respect
because
of operation,
because terahertz can penetrate, terahertz can go. For example, it can go, let's say, kilometer or more because you don't have any attenuation, you don't have low density. That's I mean, that's what advantage people use for space application, right? And for a spectrometer, the point was I mentioned that the photons they emit in this range, so they can detect. So keeping that in mind, but even after all this, people did use and people did try to use this terahertz. For many things, for example, they have low photon energy as compared to this, and so it's not harmful. So it's at least non-ionizing. This see-through capability, again, it is relative. So they can penetrate clothes, cardboard, and so on. That means, again, it has potential for security. The same way that millimeter wave, terahertz is one step ahead, provided that you can justify the cost. Because terahertz will have better resolution, and it can, because they have high loss in moisture, but anything in clothes, unless you are fully wet or something, it is fine. It can penetrate the clothes, it can penetrate even plastic board or something. So anything, for example, if even this box, this is just very thin thing, and it's not not glossy. So I can use terahertz also to see what is inside. So that application is fine, that works. So there is no doubt on this. Then what we have, what we call the Terahertz signature. That's something actually again for security applications. This is very having high potential for defense applications. The idea is that all the harmful materials, they have a specific terahertz what we call signature or dielectric fingerprint. So that is actually people are trying to use, that if you can find out, or you can find out that terahertz single what we call even signature of all these explosives, then that will be a very good thing, which is a new technology which can be used in order to detect this harmful explosive. And then again for security applications, that is there you have a fine, and of course no doubt that high resolution and high bandwidth. So there is no point. The constraints, as I mentioned earlier, you have losses in the in the environment. This first point, lack of guiding medium means how to propagate. Optical fiber you don't have microstrip, you don't have the waveguide. People even millimeter wave people use waveguide because anything planar doesn't work. FIW also people started working, but still it's not beyond few millimeter wave band. So that's very important challenge, that how to make structures which can guide this. This is I mentioned here high losses. So data link, what people say, oh I can make high speed data link, that's again a philosophy, a concept which can be realized. And for all this, of course, this point is that you can use it to detect cancer or tumor. This is but then again it can't penetrate much, but this is being used to detect skin cancer. That is a very good what you call skin carcinoma. Yes.
But this limitation can be overcome by having high power portable thermostats. And you can increase the power so that the depth of penetration will increase at that particular frequency.
How much power you can achieve as of today?
Means at 1 watt or around 100 milliwatt of power, terahertz frequency range. If it is possible, then this limitation can be overcome.
Which limit?
This high absorption in the water contained.
Yes and no. Yes, you are right that if you have high power, you can penetrate more, but you don't want to heat. You want to image. So if you have a watt of power, and that to concentrate in a region, it can even heat the tissue. That's why all the imaging techniques they use very low power.
But the heating will depend on average power. Since I am talking about peak power of this terahertz signal, the heating,
if you have terahertz pulse of thing, yes, pulse power you can use, yes, right. Pulse power. So that way increase resistance, yes.
Heating will come into picture once your average power.
Yes, increase, yes. So if you have high terahertz peaks, if you can have this, then it can be increased, yes, that's true.
1 watt of power you mentioned, is it achievable in terahertz?
There are some papers, and we are also working at CD Pilani. We are working on this portable.
Up to like 100 gigahertz.
What 200 gigahertz at this 200 we are targeting, and we are targeting for generating a peak power of around 1 watt or 210 watt. But we are still in R&D phase. We are trying to.
Which source you are using?
Sir, it's a plasma-based terahertz.
Okay, yeah. If you can have terahertz pulses of high power, then yes, that not overcome, but that can be increased. Yes. So again, the same thing. The important part is the cost. That is it possible to have equipments which are economical? You can use, for example, for some specific application which is strategic application, defense application, but can it be used for commercial application? Because there the cost is a very important aspect, and that is something actually which you have to put in mind before you want to go for this. Okay, so I think we have a break and then we meet again next year for tea. Okay, good. Terahertz. Now, terahertz as of today, there are two main aspects. Where is my pointer? So, what we call spectroscopy and imaging. So, when you say spectroscopy, it means we just want to know the absorption and emission by the metal. That means again, sort of we can say this is for like what we call simple material characterization, and imaging the same way the RF or what we call the terahertz. So usually this is important what we call terahertz spectroscopy for simple reason that, as I mentioned earlier, most of these materials, especially these explosives or these materials what people say, they have different dielectric signature. So that means if you are able to get their dielectric signature, even you can call footprint or something like this, then it should help you in order to identify the material based on their Terahertz signature or Terahertz emissivity or whatever you can call. And this comes in the purview of what we call spectroscopy. And if you want to get the image of the object, I will call it imaging. And this is a standard that people use. This is just to show the problem. If you say the atmospheric attenuation, you see that it's really very bad in terahertz range, almost like there is no transmission. And that is why this is not really a good choice for normal ground station, where you have density is high and you have high losses. And that's actually you should understand before you start working on terahertz. And you can see the absorptions. For water, see is very high. Of course, metal like high, almost 100% effectivity. If you compare plastic and water, no, it's like almost 2 or 3 order or something. So that gives you the impression that why you can use terahertz for imaging where something is contained in a plastic container, but not for anything. Biomedical thing is challenged because of high absorption, and we know that all other tissues are having more than 80% water. So that's the main challenge, that how to use it for the normal biological things. Semiconductor is something between what we call the plastic and the, but it's still fine. It's not that bad. The main problem is anything it's humid, having high water content or something, it's difficult to penetrate, and so that's not very easy to obtain. So applications, as mentioned via astrophysics, this was a starting point. Still now people are using it for space, plasma. So you are using it. This is used quite often. Gas spectroscopy, non-contact testing. Security is something, as I mentioned earlier, it's very useful to detect explosives. Biomedical sort of skin imaging, skinning of. This is also very good application for drugs formulation, because it's like you have a tablet, you want to see its content. There it works very good, and people are using this. This is also a very good application. Paint layers in automobiles. Like if you have high-end automobiles, people want to also actually know in very accurate way what is the, if there is any corrosion which you can see from naked eye. There terahertz is very useful, because if you have even like micron thickness is there, you can find out. So suppose even if you don't see it from the top, but say just below 20 or 30 micron, that you can use terahertz in order to find out what they call the subsurface imaging of the paint using this terahertz thing, and that works. So that's actually very useful. People are using this automobiles, and similarly like inspection of buildings. Same thing like millimeter wave, except for the fact that in this case you can have better resolution. So there's something actually they are the application measure which people are trying to explore. So biomedical thing is challenging, but many applications which are like skinning of drugs, automobiles, gas spectroscopy, they are this explosive. They are they are practical. They are being used actually. So if I say simple, what we call spectroscopy is simple. It's a very most simple thing which you could think of. You have a sample, you have what we call terahertz pulse going there, and you just see how much is coming back. So you just measure what we call the transmission, and from these like multiple peaks, you try to find out what we call a sample properties. It's something like a characterization. So you can have either transmission mode, where you see how much terahertz is going all the way, or you can have reflection, where you just find out that you just send signal and how much is reflected. So both the models are being used. Again, it's also being used in normal RF and microwave, because and both have their advantage of pros and cons. In this thing, for example, you don't have to put anything behind this. So this can be used where you don't have access to the other side. On the other hand, for this particular application, actually you have advantage that you can measure both transmission, you can also measure reflection. So this is something, and from this reflection, you can try to find out what we call how much was the property of this. And this is just the same thing that if you take, and usually terahertz source, usually even now people are using time domain. So if you want to use its property as function of frequency, you can take, for example, FFT, and then you can see that you can find out its value over a function of frequency. So terahertz, this again is very important aspect, that if you want to design a system using terahertz, there are two approaches. One thing is that if you buy network analyzer, they give you multipliers, works up to say 1.1 terahertz. And this is concept is simple, that you have a normal network analyzer, you go on multiplying until you get 1 terahertz. This is one aspect, and this is usually used by most of the engineering institutes. Other aspect is that if you are a physicist, usually you have what we call a femtosecond pulse laser. So this is like you have a time domain pulse, and you want to excite this using this time domain pulse, and you want to get the response, whether it's diffraction and transmission mode. And in this case, because you are working in time domain, so if you want to use the data in frequency domain, if you use FFT, and on the other hand, if you use like terahertz, and both have actually their pros and cons. And also, again, as Professor was saying, whom do you ask? If you go and ask engineers, they say, oh, this is very good multiplier, femtosecond pulse laser is not good. If you go and talk to physicists, they will say, oh, they have a lot of noise multipliers, and pulse laser is good. So, but anyway, both are them used depending upon what you have, but both are expensive. They are not that easy to achieve. So that's the main challenge. This is something like one of the experiments of terahertz that people achieve. This is, you can find, this is a normal, this is the very famous paper. Just like there was a chip, and people could image this using terahertz. It's just like simple, what we can say, the simple transmitter. This is like a normal chip. They can get all the pins, this 2D image of this using this normal, and as you can see, this is femtosecond pulse source. This was that time. This was the main. This was more popular because this multipliers came afterwards. So that's why they could use this pulse laser to excite, and then you, on the other hand, you just get what we call the transmission, and then if you just plot this on 2D scale, you can get the image. Then just to show, and because the idea is that you can see inside, and because it's a plastic packaging, so as I mentioned, they have to penetrate the plastic, so you are able to get actually the image. So that was very just to show that terahertz can penetrate plastics, and this was being used in the early days. Again, just for fun, that if you have a leaf, so just to show that this is a fresh leaf, and this is after 48 hours, so you can differentiate. And concept is simple, that it's become dry. So you have different moisture, so you have different terahertz property. That's it. This is again, as I mentioned there, the cardboard. So this is like, this is interesting that if you have, this is like a shoe, if something you hide in the shoe, and if you go with above the terahertz thing, you can actually see. So this is actually very good practical side. There's something, if you hide in a cardboard, or your shoe is not metal, so it can penetrate the shoe, and this image you can, and this you can say this is pretty sharp image. So it does show that you can detect and identify the hidden object. So this is has a potential that it can be used, for example, security application. So that is actually is very useful. Again, for security, so it's something you hide behind T-shirt. Normal image you cannot see. If your terahertz image, this is optical image, and terahertz you can see that something is hidden clearly, that there is some type gun-shaped object is there. So this is again is simple terahertz without doing any processing. Just use terahertz, scan, and get the image. So they are just provided you have the source and you have the receiver. And this is the explosives that, and you can see there, all of these, they are explosive materials, and you can our aim to show that each of these RDX, FEP4 and so on, they have a distinct terahertz signature. And so that means if you can have them in your library, and if someone is taking this, you can compare the library and you can say, oh, this is something like dangerous thing. So that is a standard way to classify different kind of and detect different kind of explosives. So this is also being used here to show that they can be identified using this terahertz time. This is again what people have used to detect the skull, to say that they can, this is what we call the radiograph, this is terahertz. So you can see there that this is using X-ray, this is non-ionizing, but this is still the quality of the picture is, I mean, almost the same. Sometimes the contrast is better as compared to here. This is to show that there is, for example, yeah, and here the good thing is to see that there was some problem here in, that there is some crack there. Here you cannot see if you radiograph, but here you can see more clearly that there and this is the white portion. There is some sort of like what you call the corner structure, or there is some sort of a small, very small pin-like crack which you can identify with terahertz but not with normal radiograph. Just to show that this works. For some cases, but the radiograph doesn't work. That's the practical aspect. And this is again, people have done some study to show that if you have a so this skin thing which you have basal carcinoma, then actually also you can identify based on their dielectric properties. So you can see there that the different regions show different colors. It means that, and one of them, this also you can do simulation to show that they will have different terahertz signature or terahertz image. So this is something like for biological applications. This was people have used to show that if rather than doing X-ray of your teeth, if you do terahertz, then also you can try to find out that okay, there is some cavity there. This also you can use using the what we call. So if you have normal image, you cannot see, but if you have terahertz image, you can try to see that there is something inside. So they have is being used commercially. So this is not that bad. Idea is again simple, that terahertz might be better option than X-rays. This is something to show that how you can try to use, for example, terahertz time domain thing for the human for blood. So just to share that as compared to other liquids, your blood will have different properties. So this just, as you can see there, that if you plot this index as a function of frequency, so you can see different curves and showing that there is some difference between what we call the normal liquid and the blood, and that actually is can be used in order to wider scale for the biomedical imaging if you can penetrate. Yes.
In the previous slide, previous to this,
Hmm.
so these are the two methods. One is like from absorption data, and other one is from time of flight data.
Mm-hmm.
So what is the difference between?
Absorption means, it will be like a transmission. If terahertz is going, how much is being absorbed. And time of flight means you get only reflection. So you see the sender pulse and one reflection, second peak. So from this time you try to find out this. Okay. So you can have, as I mentioned earlier, you can use both reflection and transmission method. So depending upon which one is available, which one is more practical, which one you can access. So there are many things which can be used.
In the absorption data, we will see the
Transmission.
transmitted.
Exactly. Yeah. So you have a transmission going all the way, other side of the receiver, and you see how much thing is being absorbed. This is what we call absorption. Okay. So this is again, this is something interesting, that if you have, for example, if you burn your skin and if you cover with bandage, usually what people sometimes X-ray with doesn't work, so we open the bandage and you will see whether burn is healed or not. People have tried to explore that if you use terahertz, for example, without opening the bandage, just scan and you can actually assess that over a period of time whether the healing is good or not. This is again just to show that there are different times, and to show that if you can actually identify that okay, this burn is going better or not. So it's just a paper, you can always go and see. But this just to show that it is actually they explore this kind of application. Spectroscopy, I won't talk much. It's just like the normal equations where you say that whether using reflection or transmission is actually the same as if normal microwave. So idea is simple, that you are in time domain, you see different peaks, and then from this you find the material properties. In frequency domain, you try to measure over a wide band reflection or transmission, or both, and from this you have some set of equations, and then you can use either closed form solution or optimization approach in order to extract material properties over the wide band. So this is just the equations which you can use this. So I won't, and this is you can also try to validate numerically, and this is also like, it's valid for any kind of thing. So if you are working in terahertz, and say if you don't have the facility to measure, you can always do, the simulation. For example, let's say you use a normal CST. So I design some material, I know its properties, I can feed in the simulator, I can get reflection and transmission over the band, and then, as I mentioned earlier, whether this is imaging or spectroscopy, it's the inverse problem. For example, even if you want to know material properties, you have to extract from the transmission or reflection coefficient. So now, usually what we do is, so for example, if I give you a material to find properties, there are many methods. Simple, for example, I can put in a waveguide, I can measure reflection and transmission, then I use some equation in order to extract its material properties. Now, what you can also do is that if you don't have facility to measure reflection and transmission, let's say in terahertz, but you have written a code, you have written an equation, and you want to know whether equations are correct or not. So you can use any standard software, for example, let's say CST. You go and simulate that material, let's say of given material, you get S1 and S21. Now you treat those S1 and S21 as if they were the experimental data, and then you use those data in order to check your algorithm, because there are two independent things. One is your standard simulator, other is your handwritten programs. This is the direct program, gives you S parameter data, and this is here which you use this data in order to extract the material property or the object image. So that way is very good way to check whether doing is correct or not, and to be more authentic, because simulation can give you very accurate data, but always has some error. So what you can do is that in the measurement, whatever you do simulate, for example, you can add, let's say, 1 or 2% error to look as if it were error prone data, and then you again try to use your own algorithm. So the good thing would be if you use this approach. So one of the any inverse problem is that sometimes it is sensitive. Even with 1% error, you have very wide change in the what we call result. That means your problem is not good. But say if with 5% error in the measurement, you get 5% error in the extraction, that means your work is stable. That way is a good way to check to say if you add 5% error in the simulation data, and if also it have 5% or let's say 6% error in your extraction image or the properties, material properties, then you can be sure that your algorithm is stable. It's not going out of bound. So that's something very simple way to check that even without any measurement, you can check your algorithm what you have developed. So this is the same thing that you have done, simulated this setup. In this case, what we call the simple material. You feed in its properties, and then you get S11 and S21 data, and then you use this data to extract index of reflection. So this is just to show that this is the actual property, and because in this case this is the actual property, so you can compare that how far you are from the actual thing. So this is just to check your own algorithm or equation if you have derived. This is that was time domain is again the same, but in the frequency domain, in this case equations are same, except that now you are directly having the frequency domain data. Though you can have the length of this. So I won't go into detail here. Yeah. So imaging, for example, this is again one of the very simple things that people have been using for in-depth. When I say in-depth, it's not that deep. It's more like the skin. So it's up till now, people see potential for terahertz for what we call to check skin carcinoma. If you have something just below the skin, let's say few 100 microns, they are going to penetrate, and you can get. And for example, people have used this to get the terahertz skin carcinoma, burn imaging. This whole thing can be used because they are not much beyond the skin, and there terahertz is having potential. So this is just to show that if you have a, for example, sample, this is skin sample, in vitro sample, you can use terahertz to give it, and something. This is reflection mode. So this is wave is going, it's coming back, and now from this instant reflection, you can try to find out the tissue property. This is something which actually people have been trying. So this is just to show and this is to show that after 1 week, 2 weeks, 3 weeks, how much change. This is to observe that whether there is improvement is a function of time. This is again like skin has many layers, so this is stratum corneum and epidermis. So just to show that there is different. I mean, if you go to any biological model, so skin have sometimes more than 100 layers, but you can't do all. But say you can approximately divide into 2-3 layers. The first one is what we call the stratum corneum, then epidermis, and so on. So, for example, our case, anything you can model depending upon what you want to, which property you want to model. Now, for our case, if you want to model skin, whether RF, millimeter wave or terahertz, we want to model in terms of dielectric properties and dielectric loss, because it's usually non-magnetic. So, in that case, what we would be interested is that if I start going from skin, there will be how many layers? Maybe there are 100 layers, but we can do this. So, what we will see that, for example, if I go from first layer to second layer, this is how much difference. And so, it has been so, people have done this, that even if you take, let's say 3 or 4 layers, so the first 2 layer is a big difference, afterwards there is not much change. So, I can still take it's like a semi-infinite medium. So, that's something you can try to model, and you can see, are you able to see this, see the effect. And this is a normal device thing, so you can do a function of frequency. If you just measure at high frequency and low frequency, the F infinity is means, for example, let's say you measure at 1 terahertz and you measure at megahertz, so you can just, by these two things you can make a model and you can obtain tau 1 and tau 2, so that like an epidermis is actually the most outer skin. So, you can obtain its property over this, people have done this. So, you can use this data in order to obtain a skin model over a wide band. Once you do this, then actually you can try to obtain the effective index as a function of frequency. The same equation. So, this is an idea here to show that if you have a normal skin, this one is a normal skin and this is a skin with the what called basal cell carcinoma. That means in the range of terahertz, you can detect the difference between healthy tissue and what we call malignant tissue due to the fact that they have different dielectric properties. Of course, when you try to measure, then the main thing would be that how accurately, I mean, there is how much change, because ideally the more difference is better. So, what we call the sensitivity. So, that means if you, for example, if I say that the effective index of normal tissue is 2.2 and if I tell you this is cancer is becoming 2.8, difference of around 20%, that's better. But say if the difference is around 1%, no, it becomes difficult to detect. So, that way we always look for those methods which can try to detect minimum change, and minimum change means like we will only measure the, let's say, effective index. So, we want to say that for the minimum change in what we call the all property, in other words, so we will look for a device where we can observe big change into between the normal and the cancer tissue. For example, if I have measured reflection, if I have big change in the reflection between these two, I can see, okay, this is a healthy one, this is a not healthy one. This is something what we can try to obtain. This again the some modeling parameters for this. This what people have been using. So, this is just like a simple terahertz probe, what you see there. So, this also have an inbuilt quartz window. So, idea is that you have a terahertz source, it's going through quartz, and if you see the time domain, the first reflection is from the quartz window, and second is from the skin. That means from these two reflections, you can try to find out their strength, the time difference, and all. And if you now imagine you scan this over the range, if suppose I suspect that at some point this skin is not good, there is some malignant tissue. So, in this case, this tips will be different, and that will be the basis for. So, first you can calibrate the normal skin, and then you can try to find out with what we call the malignant tissue. And this is just based on this you can try to detect. This is again what we call showing the skin burn. So, this is this is the burn thing. So, you put a bandage. Now, you don't want to open the bandage, but you want to see without. This is just to show that if you change this after a while, then you can see that this one is actually without opening bandage, you can see that there is some burn of this shape. So just to show that this will give you some value of this is for that skin. The people have done this image to show that it can be done without doing any damage to the skin. So this actually I think I have shown there. This just I will show it briefly that for basal carcinoma, if you want to do this is just a simple model that you have 3 skin: stratum, corneum, epidermis, and dermis. So they are just, it's just like we are considering this as a 3 different layers of skin. So idea is they are simple, that skin has like water and other tissues, the protein and so on. So and this thickness is 150 micron from the top, and it's 80 micron second one, and 1 mm in the third one. So that means, and the idea, if you see there, this 50 micron, 80 micron, they are well within terahertz wavelength. So that means if you use terahertz wave, you can distinguish this different spatial region, and that means that suppose if you measure any healthy skin tissue, so this will be the same and have some properties. But on the other hand, let's say the second layer is getting damaged either due to burn or here this due to carcinoma, it will have different dielectric properties, and then based on this difference in dielectric properties, you can try to find out that this is a healthy one and this is the non-healthy one, or this is what we call a malignant or malignant tissue. This is just a simple model, very simple model, one dimensional. So you can see there that this is the first thing, what we call the stratum corneum, then epidermis, and then dermis. So they are just 3 layers, their dimension is given. So idea is that you can try to put them. They have that in CST, you can use any software, and then you can, once you use this, you know their properties, and you can try. So again, what I mentioned earlier, the same thing is done here. Without any measurement, you first take the data from the iteration, you know their properties, you put in the simulator, you obtain what we call the reflection at the surface at this point, and there you can also get transmission if you want. Say if you only measure reflection, then from this reflection actually we can try to find out if you have a wideband, the permittivity is a function of distance. So one will be for the case of what we call the normal thing, where you have healthy tissue, and the other one would be where the tissue is there is something what we call is malignant. I just show, this is just a modeling, I won't go there. Yeah, this is something which I wanted to show, that if you just measure reflectivity, so this just which first you have to validate. So this is like, this is something which people have reported, this one, the green one, and you see if you use this model, this has been obtained. That's to say that your modeling is correct. So what you are, and this is the direct problem, that for a given 3-layer thing, you are able to get reflectivity as a function of frequency over this terahertz range. Then what you can do, that what you want to do is that this is something actually which is the important part, that this is a healthy skin, and this is the skin, this is the healthy one, this is the infected skin. The top one is infected, this is one is healthy. So now what we want to say is like this. So in actual case, what you want to do is that I have, there is some person with infected skin, you will go with terahertz source, you will scan over a wideband, you will use what we call your algorithm, and you should be able to detect that this one is healthy, this one is not healthy. If you are not doing measurement, you can take their healthy tissue properties, you can take property of which is what we call malignant tissue, put in a software, get your scattering coefficient, and then in terms of scattering coefficient, you try to actually show that how the what we call the property look like. So this is the principle. So I will just show, this is a model which has been done, and this is the reflectivity. So you can see there this a comparison. So what I wanted to show is something like this, that if you use everything, then at the end this is the normal skin, and this is the skin with the malignancy. So you can see there that because they have difference in the properties, so you can distinguish one. Of course, you see depth is of the order of micron. So that means, just to show, the practical viability, that as long as you have anything of few microns below the skin, you can use terahertz, and this works whether it is for burn injury or what we call for malignancy. But if you go very wide inside, then you cannot use. So this is just to, and that one for carcinoma, the same thing actually with goat for what we call that burn injuries. Now I just try to, this is double layer model. So this is, yeah, this is just to, again to show that if you have, let's say on the skin, if you have degree of, burn of first degree, second degree and third degree and so on, and you don't know which degree you have, you can use terahertz source and you can try to scan, and from this what we call affected data, you can try to obtain. This is something which I will show here. Yeah, this is the result, that if you simulate this, then you can obtain that this is the what we call one which is not healthy, and this is some, so they are just, this is background is a healthy tissue, and these three are burns of different degrees. Idea is that you can distinguish these different burns based on their properties. Last example is, as I mentioned earlier, so this is again for thickness measurement. This is like a paint. Imagine that you have a paint of multi layers of each of micron, and suppose second layer is damaged. There is some corrosion below the surface. So you can use terahertz. The concept is the same, that you just measure here reflection at the surface, and then if you measure over a wide band, you should be able to find out refractive index as a function of distance. So the layer which will be damaged, it will show different refractive index as compared to the other one, and with the help of this diffractive index, you can distinguish that this one is, there is damage or corrosion, and other ones are good. So now I just, before I go to the next topic, I will finish this one, which, and that is something which was what we call a near field imaging. So I just wanted to this I mentioned about the characterization. So this I already mentioned. Okay, so now let's start from there. What I wanted to now show, that apart from conventional imaging, you can also use what we call the RF sensors, which are nothing but a way to determine dielectric properties. So this we can interpret as a sort of near field imaging techniques. That means till now most of them, whatever we have, except few, have used antenna. So object is there, you use antenna and you try to scan. Now suppose I have a method where I can, the way like ultrasound works. So I have an object, I go with our probe, and I can touch, at a number of places. So this kind of technique can be used also for what we call the imaging. Let's first start with the characterization. So number of methods are there to characterize resonant, non-resonant, and so on. So without going, let's first concentrate here on resonant method. So just as a passing remark, if I have two methods, resonant and non-resonant, resonant method means you want to find out material property at any single frequency. So it works very good. It gives accurate value, but it's only at one frequency, and but the advantage is that it is having high sensitivity. That means if you want to know very accurate value, you should use this, but it will give one frequency and you design the cavity. On the other hand, non-resonant methods means you, with one measurement, you can obtain property over a wide frequency band. This works very fine because there you measure reflection and absorption coefficient over the band, and then at each frequency you try to obtain permittivity, even permittivity also if the material is magnetic, using some algorithm. Now our aim is to use this for imaging. Now imagine that, or let's say even for characterization also. So in this case, let's see how it works. So in resonant methods, it's simple. that you just have to you have two parameters, resonant frequency and quality. And this is, you know, any resonator, whether it's cavity or normal thing, you have two parameters, resonant frequency and quality factor. This is simple scheme. So I have designed a cavity, and then I have measured first empty cavity. So it will resonate at any one frequency, FR. It will have some Q depending upon the quality of our resonator or the cavity. Now I put sample inside, whether any shape, circular, rectangular, then metal, but it should be small. Small in the sense that after I put sample inside, it should not significantly change the field distribution inside the resonator or the cavity. Once you have this approximation, what happens is that this is your empty cavity, resonant frequency and quality factor. Now after I put sample inside, both will change. This will shift and curve will be broadened, so Q will change. And the idea is simple, that with the help of resonant frequency and quality factor, change in the result, change in resonant frequency FRS minus FR naught, QS minus Q naught, you should be able to obtain dialectic parameters, real and imaginary part both. This is a simple resonator using, and conventionally is being implemented using rectangular cavity. This is how it's implemented. So you have rectangular waveguide, make this both sides closed with except a small hole which is iris, make a small hole at the center to put sample. Sample is very small, put it inside, low lossy, so it will change the resonant frequency and quality factor, and the simple formulas are there. So this is a resonant frequency, this is a real part, imaginary part. You can see there, V naught is sample of the cavity, sample volume, resonant frequency of without sample, with sample. QS is the again with sample and without sample. So everything is known. So this is the simplest method to calculate the permittivity of one frequency. This is a conventional way how people have been using. So you just design a cavity at, let's say you want to design at X band 10 gigahertz. You have a cavity at 10 gigahertz. Everything you have a two rectangular waveguide waveguide adapters. Then in between, basically you have an iris to couple this from the waveguide to the cavity, and then you measure this and you obtain this property. Now, what has to do with the imaging and how it helps? So this was the conventional thing. Now here, if I want to design a cavity, let's say at 10 gigahertz, what are the main considerations that you have to see? For example, length of the cavity. What should be the length of the cavity in terms of wavelength? So you have done rectangular waveguide, you have done cavity. So if I convert waveguide to a cavity, what should be the length? I mean, let's say if I want to design it for the lowest order mode, half wavelength, right? So if it's X band, it is 10 gigahertz, whatever lambda by 2, if the size. That means the size of the resonator will depend upon the wavelength, right? And the same, again the same thing as the imaging, where we say image size will depend upon the wavelength. So something similar. And it's just to show that this is how done practically, how it's done. So you just like you have a cavity, you have a this is cavity, it's a waveguide, make cavity by 2 iris. This is there, it's a small hole. This couples the energy from this waveguide adapter to this. Different samples put inside, and you can see there that practically if this is without sample, it will shift, and that means by shift in the frequency, you can measure the real part, and by this Q factor at each point, you can measure the imaginary part. That's something how it's practically being done. But the main thing is the size. See there, the size is lambda by lambda by 2 is for the first mode, but usually you don't take first mode, you take third mode, fifth mode, so 5 lambda by 2 for example. Why? Because you want the cavity to be larger, so that if the cavity volume is large as compared to sample volume, you have better approximation of this, that then the sample will be small. If you make it very small cavity, then sample will be still be not that small compared to size, and the equation will not be very that accurately. That's the whole thing. Okay, so you make it very so the size you see, this is for X band cavity. So such a big size to make this. Now, of course, this was a conventional one. people try to use the same thing in the planar. So if you want to transform rectangular cavity to planar, what is the way out? What is the equivalent of the rectangular waveguide into the planar? SIW? How does SIW? Substrate integrated waveguide. You just try to take a substrate and you make a via on all sides, and then this like side walls, and then you make a cavity. It's called SIW. The same thing is there. That this is like this is just to this is the normal cavity. SIW, all things is planar, and you just make a hole like this and like this. This is for one insertion, E plane. This is for your what we call H plane. You couple from the waveguide and normal SIW based cavity, except that now you are making a cavity for the material thing. So this is one step ahead as compared to the waveguide. However, still this dimension should be compared to the wavelength, except for the fact that now this is compact because the height is not that a by 2, height is very small, less like substrate thickness, and also because substrate, if you take FR4, let's say 4.4, the size according to wavelength is reduced, size will be reduced. So it's sort of equivalent of this in the planar case, and this also people have been used to characterize. So this is like you have this uneconcentric side with the coaxial if you want. That was the one with the what we call normal microstrip, this is with the coaxial. But the idea is that this is a planar structure, and because this is having filled with epsilon r, so size length d will be less as compared to the equivalent wave free space thing. Just to show how you can made it and you can put the sample inside. And this for liquids, but you can also make it for solids. Now, you can call them sensors because it will sense the active properties. So if I go back, it's like you will sense the active properties because just like you put something, any active material, it will sense its properties. So here sensor means you have a device which is a planar structure in this case, and you use it to extract the active properties. That's we are calling, and because the active property is active property, so we are calling the sensor. Now the new concept is what we call the material inspired sensors.
In the planar technique, you have a cavity.
Yes.
But whatever you're trying to measure has to exactly fit into the cavity, isn't it? Because if there is a air gap, then
no. I make a cavity. Let's say this is a cavity, planar one. Now I make a hole and put something inside.
okay.
Same thing like a waveguide based cavity, except that this is now planar. It's not a waveguide.
But no, what I'm saying is
Ah.
your planar structure
Yeah.
will be specific to the thing you are testing, isn't it? Because
No, there are two options. One way is that you suppose you want to test FR4. You directly make cavity there itself. So then that's what you're saying is true. But we can also have a configuration where I can make a cavity of FR4 and I can make some other material. In this case, I just make a hole and put material inside. So we can have both versions. Okay. So the next one is more versatile because then you just make this, except for the fact that in this case we have to ensure that the material itself is having low loss. For example, like if you FR4 not very having low loss, in this case it's not that good idea because if you have anything having low loss than FR4, it won't give you great value. That's the challenge. Otherwise, both the options are available.
In this, the sample has to be of exactly the same shape so that it can be inserted.
In this case, yes. So if you make, for example, external sample, if I say let's say circular thing, so usually then you have to put sample inside of the same size, and also usually should put a tape afterwards so that everything is enclosed. That gives you accurate results. Of course, if you measure liquids, then that's a different scenario. But again, because liquid is lossy, so if you put it much higher than this, so the effect will be smaller. But then size is according to wavelength is reduced, size is reduced. However, still that lambda by 2 thing is there. For example, if I want to make a SIW based cavity at 10 gigahertz, if I want to use fifth mole, it will have to 5 lambda g by 2. Lambda g is lambda not by not epsilon r. That limit is still there. Now, people said, okay, we want to make more compact resonator, what we call electrically a small resonators. And this can be achieved using what we call metamaterials. Metamaterials, probably many of you have worked on, right? How many of you have worked on metamaterials? Yeah. Oh, not many. So, okay, so I won't talk about much about this. Just this is a concept like normal material, except that they are artificial. So, like normal material. So, if you see to be more specific, so they are some of this, 1, 2, 3, 4. I just explain in very brief way. So, in normal material you have molecule and atom. So, for example, if I take a Teflon, whether you take material of 1 centimeter or 1 meter, should give the same property, epsilon r equal to 2.1. It can't happen that it depends on size, right? So, now if you want to define artificial material, the moment you can call material, it means it should have the same property. So, whatever size you take should give you the same electrical properties. Now, we don't have atom or molecule, we have what we call unit cell. And the unit cell size should be small as compared to the operating wavelength. For example, if you lambda by 10 or even lower is better. If you have this kind of, if you have this situation with you, then if you try it, for example, if you go at micro level in also in normal material, you will have proton and electron, and then if you say property of electron or proton, nothing works. We don't have permittivity. Permittivity is a property which is macroscopic, it is not microscopic. We don't go at the micro level. Exactly the same way, let's say this is your, this is like, take one of them. This is a metal, one ring, outer ring, inner ring. If I go inside the ring, what we do? This is metal, this is dielectric, there is a gap, non-homogeneous, no property. However, if I see this as a whole, and if I consider one of them as our unit cell or atom, then it is continuous. Then it is a material, because provided that if you assume that each of these have very, very small as compared to the wavelength. The same way you have your atoms are very small as compared to, for example, if I take, I will not take, if I want to measure epsilon of material, I won't take material of 1 nanometer. I will take at least a millimeter, depending on the wavelength. The same way here, that if you want to characterize them, you take at least a number of them, for example, 10 into 10, and then you put it, then it's like a material. So, but if you go beyond the unit cell, the materials are not uniform. So, that's the whole concept, that you replace atoms or a molecule by a unit cell. If you go beyond unit cell, it's like a microstructure. Same thing, you go inside the atom where you have electron or proton. However, if you come beyond unit cell, it's a unit cell repeating, unit cell dimension is small compared to wavelength, this becomes like a material. But it's not material, yes, it's artificial, because you have metal, you have dielectric, and you have tried to define one artificial equivalent of a normal atom or molecule. That's why we call meta, means it's beyond materials. Now this they have been artificial structure, they have been used for many properties. You can have number of flexibilities, and so I won't go into detail, but except that they are materials, but they are not real, they are artificial, and they have unit cell equivalent to what we call atom or molecule. Very simple example to say that if a normal material you have like this structure, if you have this thing like we make rings, something like this which repeats, is like a metamaterial, because if you see each of them, you have metal, you have dielectric, you have gap, but if you see overall, it's like a material, and it's like a metamaterial. Now, our thing, why you want to use this? Basically, the first thing is the response. So the way that whether I take a small piece of Teflon or larger tip, same is, you should get same response. The same thing is for metamaterial. Either we take, so you can only define this material in the sense that whatever a small, that's why as mentioned, you should take at least 10 by 10 or 5 by 6. If you take one unit cell, it won't give you correct value. So idea is Of course, now you can simulate this by taking one unit cell and by having unit cell boundary condition, that works. But usually, if you see practically, means you should have thing which is continuous. So you can only say it's material when you find permittivity epsilon and epsilon and mu. And mostly they are also called functional materials. And idea is that if you make it artificial, you can show at in some frequency range the properties what we call they are resonant. At some frequency they show negative mu and negative epsilon, and that's why because of, you can see the details. But basically idea is that they are extraordinary properties because they show negative epsilon and negative mu, which can otherwise be obtained from normal materials. Anyway, our interest is something else. So now we want to have resonators, and to be specific, we want to have electrically small resonators, so that we are one step ahead than the idea where we mention that the size of the resonator should be proportional to the wavelength. As long as you have this dictation that size is function of wavelength, you have normal resonators. And this is the same thing was SIW, except that it is compact, but still length is wavelength function. But if I go one step ahead and I say I have this, and there are actually sets of metamaterials. This is what splitting resonator, complementary. What if you see splitting means what? If you have a normal ring without any gap, like a loop, to have some inductance, right? But if I want to have a resonator, you have both inductance and capacitance. So now if I put a gap, it will have that capacitance. That's why it's like you can, and we have two of them, it gives you better property. Even one of them is also fine. We also have a, because it has both LNC, normal AC resonator. Okay, so splitting resonator means like I have a normal substrate, the white portion is dielectric, and this gray portion is metallic. So I have a normal substrate, normal microstrip line, even any substrate, and I make this structure. I can call it a splitting resonator, and you can show by finding that it will have negative epsilon and mu at some frequency. But anyway, even if you don't want to show it, that's fine. But we say it's a resonator. At some frequency, it will resonate. If we say complementary, complementary means what? Now we are saying, rather than doing this, we are making the reverse side of the microstrip. If you know about the microstrip, this is full metallic. And on the metallic, now we say this white portion is the dielectric. That means now, other than saying metallic structure on the substrate, we are saying dielectric structure on the metal. Therefore, of course, it's complementary. Both of them are fine. You can show that they have these properties of like a metamaterial. That's why we call them metamaterial, because they are basically metamaterial inspired. Now, we want to use it first for material testing. So what we have achieved, and size of this need not be actually, I mean they are actually small, because you know that it's not lambda by 2 thing is not now valid anymore. Even at 2 gigahertz, I can make or design very small resonators, because they are AC resonators. L is provided by this metallic ring, C is provided by the gaps. And this was the first step what people, I mean, did propose in the last 1 decade or so, even also for characterization or testing. Like rather than having a big size normal resonator, let's go for SRR or CSRR basically. They are SRR or CSRR based resonators. And this is something, so this is was people propose, but our main thing is something like this. So if you can see it clearly, this is like a microstrip, and I just make something like this, a resonator on the top. This is normal typical splitting. So for example, this is like a, and this is like backside, this is complementary. So if I put on the top side a metallic ring, this will be a what we call a splitting resonator. If I put on the backside, it will be, and this is like a many of them put together. These structures actually they are called what we call SRR, CSR based resonators, or we can also call them metamaterial inspired sensors. Now let's see how they can be used to sense or determine the material properties. So basically, if you try to design them and find this property to show resonance at some frequency. For example, this is like shows at 2 frequency, one here and one here. So now if you recall, the whole idea of resonator based sensing was starting from waveguide, that we designed a waveguide based cavity, we found out resonant frequency and quality factor, and now we are saying we have designed SRR which is splitting resonator, and we have obtained what we call the resonance, because at one frequency showing a dip like resonance characteristics. So now we have got equivalent of what we call the cavity, but using a splitting resonator, size is small as compared to a wavelength. That is called actually splitting resonator. Now we have to use it for characterization. So this is just to show the current direction, because if you want to have a splitting, one should be outside, that should be inside. If you go and simulate in any simulators, it shows this kind of field. This you can verify using any simulators. If you have complementary, it means that you are having on the reverse side, everything is same except for the fact that now this is metal and this white part dielectric. Now there is one difference. If you know electric field of microstrip line, field goes from top to bottom. So if we are having any ring on the top, this is SRR, but you know that electric field will be very small on the side. Electric field goes from top to bottom. If I have microstrip line, goes from top to bottom, so there is field in maximum center, but if you go outside, field is not that great. On the contrary, magnetic field is confined to the outside. So if you have any material which is dielectric, you should put it at the position of maximum electric field. So if we use SRR, is on the top side, is coupled to the line through usually magnetic coupling. So there if I put dielectric material, electric field is not that great. So it will not show very high sensitivity in that direction. On the contrary, if I make these rings exactly on the opposite side of the microstrip, here electric field is maximum at the center. So it will show that my electric field in CSRR is much high and it's much more concentrated as compared to that of the what we call SRR. And that's why they are better suited to test dielectric material as compared to the normal SRR which put on the top, because here electric field is more. And that's why usually for electric field, for dielectric measurements, we use this. Now let's say how we use for the, this is just equivalent circuit, that if you know you have basically LC, you have 2 capacitor, this is 2 capacitor, and basically at the end it's like L and C in parallel. And if you have losses, you can also encode resistance. But this is whether you have complementary or they both have L and C thing at the end, because this can combine into one. Now usually this is the equation for normal cavity that as I mentioned earlier, that if you want to see how much change in the frequency as compared to the electric field. Let's come to our thing, that if I have CSRR, means I have put this on the back of this microstrip. Now it will have some resonant frequency. If I put some material on the top of this, what happens? Frequency will shift. So that means rather than going and designing a waveguide based cavity or other cavity where you put sample inside, now sizes become compact and you just have to put sample on the top of this. So even sample machining is not required. Any shape sample, just like put on the top, minimize the air gap between this, and you will get a shift in the resonant frequency and the quality factor, and from this you can obtain its properties. That's the basis of what we call the characterization.
Are you putting this in the direction, at the side of the slide or the?
No, just on the top. So this is your microstrip.
Yes.
On the back side you put this what we call thing, on top you put the material.
Okay.
Yeah, on the top of this. Yeah. And it will show the shift. So you can also see there. This is your substrate, and this is your ground plane, and above this you have the microstrip. This is the material in the test. And you can see there, if you do this, and of course, because now everything is changed, you have different configuration, you don't have any regular shape, so it's not easy to use closed form formula. So in this case, the best thing would be that you use a simulator, you find out, let's say S21 or resonant frequency as a function of, for example, you first simulate without any sample, you will get the resonant frequency FR0. Then usually you will imagine the sample which you test will have range between 1 to 20. So you use all these cases, you find out for each case what would be the resonant frequency. You try to plot resonant frequency versus option R, make a set of curves, do this curve fitting, get some equation which will give you option R in terms of shift in resonant frequency. So that's something like different from the conventional way, because then here the advantage would be that you have more coarse thing which is suited to a particular structure. And so that is more accurate than the normal conventional one, because this is irregular shape. But once you have this, then you can make this equation, and then you can, for any resonant frequency you can get back and you can get the perimeter to the sample. So this is something, and this is just a model. So you have here, this is a microstrip, this is your CSRR, and they are coupled with through the a normal capacitor, because you have a top and bottom of the metal, between you have a capacitor. And this is like you can just show this is the equivalent circuit model of your CSRR. And so once you have this, actually you can see if you load with different materials, it will show different shift from here to here, and from this shift you can actually obtain the option R just for different samples. So this is again the same, you can get equation either, also you can also get equation of the second order, third order, that also works fine. It's just show how you do it practically. So you have designed your sensor, microstrip, bottom side, put this side here, put bottom on top, and then you measure shift in frequency and you measure this. Okay, this is how you do it. This was for normal characterization, and this works. So size is compact, and you can use many materials, and you can see there it's very simple. Just put on top, nothing to do, and it works quite fine. Now we want to use for imaging, and especially for near field imaging. And concept is very simple. So what you do is that rather than now I am saying that I am having, let's say I am having some sort of checkbox. So if I see this 2D plane, I see it has different materials at different points, and I want to test using our sensor. What I will do is I simply go with our device and I scan the whole area using our what we call our sensor. And this is what we call, so this is different from the conventional imaging scheme. What is the advantage? First thing is the resolution. We mentioned there that resolution depends upon the wavelength, and now we have got a device, sensor in this case, which is practically a small resonators. That means now our size of the sensor is not directly depending upon the wavelength. It's small compared to wavelength, and that means, and our imaging in this latter direction will be dependent upon the size of our what we call resonator. So now if you think for a while, you can see that you can get resolution which is much better than your conventional wavelength limit. And that's why you can also say that if you use this near field SR based imaging scheme, it will give you what we call the super resolution kind of imaging, which is not limited by the conventional wavelength based scheme. That's the one thing why people are trying to explore this. That is simple. It is having what we call the a very simplified approach. Hardware is simple, you have seen there, simple arrangement, and the main thing is you get much higher resolution as compared to conventional wavelength based limitation. That's something actually people are trying to use. So we did it for some number of cases. So the concept, for example, and let's say I want to use, for example, I have some defect, say, for example, a paint. So I have some, let's say, what we call, I have some concrete, something has gone down behind the concrete. So I can go with my sensor, I can scan the area, and so wherever there is, without any causing any damage to this thing, I can see at which point there is some crack or there is some defect. So there's something which it can be used. So we can use the defect of the subsurface force inside it without putting coating out. That's something the concept is not used. This is actually, for example, like you have a corrosion in aluminum. So you coat, this is like this is our sensor which say you use. You design a sensor first, normal sensor, nothing, and you just check this, and then you go and this is something the topology. So you have a full aluminum plate, this is your sensor, and now let's say this region is something where this is damaged. So what you do is that this is your sensor. In this pattern, you try to scan the whole area, and if you scan the area, then what you will observe is that at this point when you reach, you will see different resonant frequency, different S21 as compared to other region. And then if you try to plot that data over this 2D plane, you will get as if the 2D image of the structure without touching, without actually going, without taking this outer thing out. That's the whole philosophy. For example, this is like the two things. So this is like your this, the other, for example, this is the normal aluminum thing. There are two regions which are having corrosion, and you just coat this with Teflon. Now if you just coat this with Teflon, you can see what is inside, and then use this scanner to raster scanning, go over the whole scanning, and then if you scan this and if you plot, let's say, phase and the magnitude of this, you can see there that this area, I know you can measure S21, amplitude, phase, everything. So if you try to, for example, use this S11 magnitude or even the phase, you can see there, a computer background, you have something which is like a defect or anomaly in the structure, and this is something like it's using this kind of sensor. So this is just very simple scheme to show that you can actually obtain the defect inside structure using this SRR based sensors. This is again the same thing which then you have what you call the cracks. For example, let's say this is a crack inside this metallic block, above is hidden, you don't know where is the crack. The same thing that you try to use what we call the resonator, and you put it, you scan the whole area, and then after which you plot this. So this is to show the reference value, that what you expect when the air, when there is difference and there is crack. So this is like, this you can do in advance, that what do you expect, and then you can go and you can go back, compare with the data. And if you plot this, you can show there that this is the crack which you expect. This is the surface. This is a simulation to show that how the surface current will look like at this particular frequency. And this is, if you do this, you can also normalize that crack width also can be determined by the function of the resonant frequency. So that means both the width presence and its depth, they both can be determined using this approach. Can also be used, for example, to detect composite structure. Composite means now you have dielectric, metal, everything put together. You don't know where is what, and we want to image using our, and you know that you can have both shapes. You can have either rectangular or circular. Any kind of sensing, whether you have circular, resonator, or any some sensor, what is the most important parameter? Let's say you want to, at the end you are measuring resonant frequency. Now there is something what we call defined as sensitivity. In this case, it will be defined as a parameter which will tell that for each unit change in resonant frequency, there will be how much change. So there are two parameters, resonant frequency and let's say the permittivity. Now you are observing resonant frequency. From this you want to extract the permittivity. Your objective would be that, let's say, if you want to go from permittivity of 1 to 2, it should show maximum change in the resonant frequency. They only you can, because let's say you go from permittivity from 1 to 2 and the frequency shift is from 1 gigahertz to 1.0001 gigahertz. You don't know whether this is anomaly or is actual value. However, you have other system where if you go from inner frequency from go from the permittivity from 1 to 2 and you detect a shift in frequency from let's say 1 gigahertz to 1.1 gigahertz. That's perfect. You have around 100 megahertz shift with 1. That means if you have a value of around 1 to 10, you have more shift. So ideally, simple thing is that for unit change in permittivity, you want to obtain maximum shift in the resonance frequency. So that, and let's say it is having higher sensitivity. And this is for any kind of sensor which you want to design. So and if you do, and so thus for example, if you go and check, it has been observed that if you have rectangular one and circular one, it gives you for the same physical dimension, circular gives you better sensitivity, for example. And that's one of the things which you have to put in mind if you design things sensor. So this is something like what. So we have two things now: circular based sensor, rectangular based sensor. They are being fabricated, and now you have what you call a test structure. So this is in between you have a defect. Now we don't know whether defect, so you put this inside. Now what you can do is that once you have this, you can either you scan sample or you scan the sensor. In this case, because sensor is more sensitive, you fix the sensor and you try to scan this sample over the whole. That means each part of this sample will come at one time over the sensor area. So that at the end you have raster scan of the whole material. And this is something like how it had been done. You fabricate the structure, put something inside, and then there are three examples. The first example, you can see there that you have a dielectric, both are dielectric. This is also background also and this is also, but they have different permittivity. The other one is you have metal and you have dielectric. In each case, you put one Teflon tape at the top. Then now from top you cannot see where is this thing. And then once you put this on the top, then you try to move your sensor above this region. That means, so if you are able to find this defect which is hidden inside using your sensor, and that means you are able to image this 2D imaging, and if you are also able, and if the image is sharper, means you have, that means first thing is that you should be able to image. Second thing is that if you want to image with a better quality, there is a big difference between the normal region and defector region, and that can be achieved if you use sensor with higher sensitivity. And that way was showed that if you have circular one, is better as compared to the rectangular one. So this is just to simulate and measured S21. By this you can compare. And this is very important thing. As you can see there, for same physical dimension, you can see that circular thing is having better shift as compared to rectangular one. Delta FR is higher for the same permittivity, and that's something actually very important thing for us to know, that this circular one is better for this kind of imaging. So you have number of parameters, magnitudes, phase and shift. And this is just to show that if you scan this is the actual practical data. So that means you can see there that where you have defect, you can easily detect the defect as compared to background, whether you use the amplitude, phase or shift in the frequency. So in all the three cases, of course in some case could be phase is better or could be shift is better. However, in all the things it is actually established that you are able to image or get the 2D image of the object using this kind of device. This is again some other structure which we use. This is some different structure where you have a sort of some inside. This again you can see that everywhere when I have this square or rectangle, I have shown the structure. So this was simple image. You can also find the permittivity. So this is just to show that for permittivity you have to get the equation as I mentioned earlier. In terms of shift, this is delta F is the shift which you can measure or can observe. Epsilon R is the permittivity which you extract. With this, so for this kind of thing, you first have to get this equation. This have to be established or derived using the simulation. Once you derive this simulation, then you can try to actually obtain. And this is what is actually actual data. This is using rectangular CSRR, circular CSRR. So they are actual permittivity. So you can see there the center value is lower and this is actually what was expected, that this was around 4.2, it's around 10.4 or 12.4, and in both the cases you are able to actually get the image. Lastly, some people have tried to use the make an array of this. So for example, there are 4 of them put on the same device, then you put some tissue here on the top in these gaps, and then you can obtain what we call the image of this. So this is like, this is some people other have tried. So for example, this is a 4 by 4, 4 on the top, 4 on the bottom, and then again you can use some object like there to derive this. It's just one of the lever which is being used here on the gap, and you can see there that after you put this, there is shift radio frequency, and this is the basis for what we call the imaging thing. This is a 2D array as I mentioned earlier, so you can have, let's say, it's a 1 port, other port, and you have 4 into 4 of different sizes, and all the things. That means rather than now scanning, you can put just one at a time, and so and at any one point, and you can get the image of this whole what we call topology in this case. This is what people have proposed. And finally, as I mentioned there, so if you have, like, say, a sort of checkbox where, let's say, everything is uniform except these 3, 1, 2, 3 regions where value is different. Now, if you go and scan this area, then you should be able to obtain permittivity at these 3 points using the whole what we call imaging scheme. This is again to show that if you do this, you will see that at these 3 places there are different values as compared to the background. And lastly, the same concept can be used applied to terahertz. People have used this. So if you use, and this is just simulation data. If you use terahertz, for example, then you can see there that if you have some film, only thing is, if you use terahertz thing, you can go up to nanometer or say micrometer, which is not possible for microwave millimeter wave. So the concept was the same. You design sensor. The only thing is difficult to fabricate. But how to fabricate this terahertz which source and actual device? Because as I mentioned in the beginning, for terahertz you have challenge in the what we call structure which is to be guide terahertz wave. For example, microstrip you can't use. You can't use normal size of structure. So you have to think of what could be tried. People are trying what we call the structure which is based on harmonics, but still there are many challenges which are being used. So I think with this I have finished my lecture. So if there are any questions or anything, I'll be able to answer. Yes.
That permittivity measurement that you told is low loss.
Yes, but this can also be permittivity. If the material is dielectric, you can use both permittivity and high. If also very high, error will be somewhat more, but you can in principle reconstruct. Yeah, because if you are able to measure quality factor, from this you can measure the imaging part also. Okay. Yeah. And yes.
You were studying near field imaging and far field imaging. So like near field imaging that we have keep remeasuring in the near field.
Yeah, near field measure from here you just touch. That's why it's near field. Far field means you put object where you have like a plane wave approximation. Yeah.
When you do measurement in the near field and far field.
Yeah.
We did measurement to find the permittivity in the far field also, and we did to.
Yeah, I mean usually all the imaging thing, convection one they do in the far field. No, so whenever you have antenna, usually you do far field imaging. No.
So this near field measurements, whatever we do, we get the permittivity. Still the results for, we do any transformation to the far field after taking the.
No, we don't need. Look, here everything has pros and cons. So here in near field, the problem is that you have to go and to touch the object. No, if there is air gap, it will give you some error. And also, if you want to get something depth dependent, this was just 2D image. It was not about depth dependent image. And there, if you do in the free space, you use over a wideband, you can use like the multi-layer structure. So I mean, everything depends upon what you want to do. So both have their advantage and drawbacks. Okay. Any other questions or comment?